Hey everyone, this is a 3D scan of an Allen key handle sent in by one of our viewers. It was captured using the Creality Raptor X, and in this video I walk you through how to reverse engineer this sculpture-like model with surface modeling in BricsCAD. At the end of the video, I will do a test print of the reverse engineer model to check its quality. In CAD, there are two main modeling approaches, solid modeling and surface modeling. You can work with either one or even combine both. For this tutorial though, I will be focusing mainly on surface modeling. In CAD, surfaces are built from sketch boundaries. Since 2D sketches are quicker to create, I will make 5 cross-sectional sketches spread along the longer axis of the handle. These sketches act as the main framework for 3D splines to connect to, forming across the boundary. If you try to build a surface boundary entirely by snapping splines directly onto the point cloud, the results usually come out less accurate. In BricsCAD, I will set up 2 layers, one for sketches and another for the solids or surface I create. That way, I can easily toggle them on and off whenever I need. I will also switch on X-lay mode, and in the view cube, make sure the view is set to UCS. In the 3D snapping settings, make sure the point cloud is selected. You will find the point cloud download link in the description so you can follow along. I set the point cloud size to 1 so it's easier to see. This scan was captured at a 0.15mm resolution, which means the distance between each point is 0.15mm. In BricsCAD, the UCS menu is tucked away deep in the View tab. Since you will be using it so often in 3D modeling, I recommend adding it to the top menu for quick access. From the right view, I will draw a vertical line and trace another along the stretched edge. Then I will use the align command to match 2 points to the vertical lines. From the top view, I will find the center of the handle. I will draw 2 straight lines along its sides, then use the center line command to create a center line by selecting those 2 lines. Then I use the align command to line up the point cloud with the vertical reference lines. I will repeat the same alignment process for both the front view and the right view. Now the point cloud is perfectly aligned to the mirror axis, and the hex key is oriented to the vertical axis across all planes. Finally, I move the point cloud together with the center line to the origin where the XYZ coordinates are set to 0. By adjusting the viewport to this orientation and using the UCS view command, I can draw a cutting line for the thumb rest. It looks like this part of the model was cut from this plane, but the entire handle wasn't originally created in CAD. I can tell this model must have been created with a polygonal modeling tool. Back in the World UCS, I will create the first sketch on the mirror plane. But before that, I need to rotate the UCS y-axis by 90 degrees so the XY plane lines up with the sketch plane. If I model this handle using solid commands, the process would be faster, but the geometry wouldn't perfectly match the original. For sculpture-like models, the best approach is surface modeling. It takes longer, but it captures the shape more accurately. I trace the profile using straight polygon lines and later refine it by adding curves. With practice, you will know exactly where to place the polygons to achieve smooth tangent curves. Cropping the point cloud in half improves visibility. Now I'm using the add bulge command to introduce curves into the polylines. When the curve you add isn't tangent to the next one, try sliding the vertex along the line. The curve will then blend in smoothly. To do this, make sure all the polylines are joined together. The function won't run if the lines are separate. Now we have our first sketch completed. Next, I will move the center line to the tip of the handlebar. This will serve as the rotation axis for fanning out the next sketch plane. Then I will use the break command to split the sketch over the center line at both ends. This divides the sketch into two halves. Then I will set the UCS origin on the center line, rotate the x-axis 90 degrees to align with the next sketch plane, and crop the point cloud to create a second cross-sectional profile on this plane. I'm not going to demonstrate every sketching step. They are straightforward and you will need to practice them yourself to really learn it. Next, I will rotate the UCS x-axis by 45 degrees to set up the next sketch plane. Then I will crop the point cloud along that plane to create the next cross-sectional profile. The previous sketches are blocking the view, so I will hide them by using the hide entity command. You can find it in the quad menu as well as in the top menu. Also make sure that the new sketch lines connects to the previous sketch at both ends. Or you can place 2 points at these ends. It's easier to snap onto them, and the upcoming sketches will need to start and end exactly at those 2 points. After adjusting the curves with the add bulge command, I now have 4 2D sketches. Next, I will rotate the UCS x-axis by 90 degrees to create the next sketch plane. Remember, UCS rotation has direction. Positive and negative values rotate in opposite directions, following the right-hand rule. There are many sketches that I need to hide from the view. The easiest way is to place them on a separate layer and simply turn off that layer's visibility. There is still a large gap between the sketches, so I will add another by rotating the UCS x-axis 22.5 degrees, half of a quarter turn. The more 2D sketch frames you create, the greater the accuracy when define the surface boundary. I have decided to model the finger rest area together with the surface modeling, so I went back to the first sketch to adjust the curve. Since each sketch plane was placed on a specific rotation axis, it's easy to align the UCS to any sketch plane. You can also use the UCS entity command to align the UCS directly to the curve you want to edit. I ran the remove bulge command to turn the curve into a straight line, then add a vertex and adjust the existing sketch to fit the finger rest area. I will switch back to the word UCS and move it to the center of this line to create a circle, then trim it in half. This section can't be replicated with solid modeling. It has to be built using surface modeling. Now I have enough 2D sketches to create the surface boundary. There is a simple rule. A surface should be created in smaller segments, divided at the locations where the curve changes. I will use the spline to close the boundaries between the 2D sketch lines, snapping the spline control points directly on the point cloud. You need to activate the 3D snapping tool by pressing the F4 key to snap the spline onto the point cloud, and then deactivate it when snapping onto the 2D curves. This approach ensures the spline lies exactly on the handlebar surface. If you trace the 2D sketches accurately, the surface will blend smoothly. There are two commands you can use to create this surface: surface patch and loft. For now, I'm testing it with a surface patch. In BricsCAD, I found that surface patch often creates unwanted curved shapes and is harder to control with rails. By contrast, the surface loft command performs very well, so I will use loft as main modeling tool. All you need to do is select two loft sketch profiles and close them with guide rails. You can also add additional guide rails in between to force the surface to fit the point cloud. When using the surface loft command, the sketch profiles are consumed. To preserve them, you will need to copy the profiles beforehand and move them back to their original position after using. When the surface boundary is too long, the loft command won't run. You will need to experiment a bit to learn where to break the boundary lines and where to place the guide rails. When the loft command successfully forces the guide rails, they will turn blue when selected. If they don't, it means you need to add more rails to break the boundary into smaller segments. Here I'm adding one more guide rail to force a smoother curve. You may need to switch the render mode to check the tangency of the surface. Now I'm creating the spline by snapping the control points directly onto the point cloud. Pressing F4 toggles the 3D snap on and off. You can later adjust the control points to match the profiles. Either move and snap the control points to the adjacent point cloud, or use the polar guide to move them along the XYZ axis of the current UCS. Here I'm breaking the sketch at this point to use it as a guide rail. When I run the surface loft here, I can't force the guide rail curve on the right side. It doesn't turn blue. When this happens, it means you need more guide rails, so I will add one more here, and now all the guide rails can be forced to create the surface. I tried adding more guide rails several times to better understand how the surface loft function works in BricsCAD. This is actually my first time modeling entirely with surfaces in BricsCAD. I placed the surface segment I created on a separate layer so I can quickly toggle its visibility whenever I need it. If you want a smooth, blended surface without standout edges, you will need to experiment with each segment, deciding where to break the boundary and where to place guide rails. Once the curves are complete, recreate the splines as a continuous curve, then break it again at the boundary intersections. This approach creates tangential continuity across the surface segments. Here, I'm retracing the spline with the curve shown in red. The result is a smooth, continuous curve that can later be broken at the boundary points. The broken spline will retain its shape and continuity. You might wonder why anyone would want to reverse engineer an organic shape like this into a CAD model. The reason is that models like this are often created by artists or product designers in polygon modeling software such as 3ds Max, Maya, or Blender, and it needs to be converted into a CAD model to generate a step file for CNC machining. When the boundary has more than 4 sides, you can try using the surface patch. It works well in this particular area. I often take jobs from sculptor artists who create only half of their model. It's faster to rebuild the geometry in CAD and then mirror the other half for them, ready for 3D printing. The workflow for reverse engineering with surfaces is very straightforward. Start by creating 2D sketch frames, then build 3D splines for the guide rails by snapping control points directly onto the point clouds. Test each lofted surface segment to determine where boundaries should be broken and how many guide rails are needed. Once the 3D curves are complete, retrace the spline if necessary to achieve a smoother continuous curve. For this demonstration, I didn't retrace the spline. I may prepare a smaller and less complex example in the future video to better illustrate smooth, continuous surface modeling. This example is a good exercise for learning how to define surface boundaries and where to place guide rails. This object contains a variety of curved surfaces, making it an excellent example to learn from. One important note: if your scan data isn't clean and produces a fuzzy point cloud, the spline may jump when you snap control points onto it. Sharp and clean scan data is essential for this process. This half circle surface was created using the surface patch command. Here is the final surface loft and is now ready to be mirrored. I used the stitch command to weld the first half of the surface segments together. Then I used the 3D mirror command to duplicate the surface to the opposite side and run the stitch command again. This converts the watertight surface into a solid. This hole has an organic shape, so I simply create a solid body as a cutting tool and subtracted it from the main body. Since the surface has now been converted into a solid, I can use commands like subtract, union, or intersect to manipulate it. Now I will load the model into the slicer. I print it in this orientation, but I suspect the support insufficient and the part might collapse during printing. To prevent that, I paint in addition support here, which should be enough to stabilize the print. The printing time is about an hour from what I can see here. There are no noticeable edges even without spline retracing. Here is the printing result from the K2 Plus. Because it's an FDM printer, the layer lines help hide some of the standout edges. However, if you print the same model with a resin printer, those edges will be more visible. That's why spline retracing becomes necessary if you plan to use resin printing or CNC milling. Here's my first reverse engineering project using surface modeling in BricsCAD. Thanks you guys for watching. I'll see you in the next video.